Hi guys, Assalamu alaikum. This is Arif. In this video, we are going to see how we can delay the signals using the time units as well as the number of clock cycles, first in a system Verilog program and then in a VHDL program. So this is a system Verilog program first, and in which the module name is project, and then we have defined some inputs and outputs. Clock is the input, PC for program counter is the input, reset signal is the input, and then we have outputs: ALU logic, load logic, store logic, and branch logic. So here we have defined actually the PC, it is of 11 bits. You can select any number of bits, and then we have the input 1 bit, and then we have the outputs also 1 bit. And then inside this main body of the program, in the always block, what we are doing is we are defining the int, and then we are converting the bits into the integer, and then we are saying if reset is applied, then we are saying make all the outputs equal to 0. And then we are going to say if reset is not applied, what we are going to do is we are going to check that if the integer value is lower than 500 and upper than 0, then we are going to say the instruction is ALU logic, and we are going to make this ALU logic signal 1, and all the other signals we are going to say those are zeros. And after that we are going to say if the instruction is like load instruction, and then we are going to say if the value is between 504 to 600, we are going to say implement this load logic and make all the other logic signals equal to 0. And then we are going to say similarly, okay, else if the instruction is between range 604 to 700, then implement the store logic and make all the other logics equal to 0. And then else, so same way we are going to say implement the branch logic and make all the other logics equal to 0. So it is a very simple program. I have defined a test bench as well. So in this test bench test project module, we are going to say okay, make all the inputs reg, you see, PC, clock, reset, and make all the inputs wires. This is the way we define the test bench, and then we are calling that same module inside this test bench using the same number of inputs and outputs. And after that what we are going to do is actually comment out this line for now. Then we are going to define a clock which is of 20 nanoseconds, right? This is the way we define a clock. And now we are going to give actually in the second initial block, we are going to give some PC values, the 11 bits. First we are making reset equal to 1, then we are making reset equal to 0. 4 inputs according to our 4 PCs we are going to give. Very simple program. Let me save this program and compile and run. Compilation of actually we are going to comment out system Verilog lines like this. Now this is our test bench program for, we are going to say simulate. track these all signals inside this waveform window. Press run. So this is actually our output. So once the reset is 1, nothing is on the output, 0, and once the reset is 0, it is no longer applied. First, during this instruction, this is ALU instruction, ALU logic is 1. Then this load instruction, this load logic is 1. Then store instruction, store logic, and then the branch instruction and branch logic is going to be 1. And then finally we are applying reset here again. So all the lines are going to go to 0. So this is the behavior of our program. Now if we are going to give some timing delays to these signals, how we can do it? So we are going to give 4 different timing delays to these 4 signals. So we can say "20 nanoseconds give to ALU logic." So it is going to become 1 after 20 nanoseconds. Load logic, we are going to say after 40 nanoseconds, make it 1. And then we are going to say store logic 60 nanoseconds. And finally the branch logic is 80 nanoseconds. So this is our complete program. Let's save it, compile it, run it. Go to this web window. Now let's run this program. So we are going to get our delays accordingly. So this signal is getting delayed ALU logic by 1 clock cycle. This one by 2 clock cycles, or this by 20, this by 40, this by 60, and this by 4 clock cycles, 80 nanoseconds, the way we defined. So we have just given the delays according to the number of clock cycles. And now we are going to see how we can give these delays not with the time units, but with the number of clock cycles. So what we are going to do is we are going to comment out this line, include this line. So using this repeat keyword, we are going to run this on positive edge clock once. So this is going to give our 1 cycle delay according to the clock cycle. Make it 1 this way, right? Others are going to stay same. Now using the number of clock cycles, 2 clock cycles delay this signal is going to get, because it is getting 1 after 40 nanoseconds. So 2 clock cycles delay. Go here, store logic, we are going to say is going to become after 3 clock cycles. Same number of delays we are giving, but using the number of clock cycles. And branch logic is going to go one after 4 clock cycles. So this is our complete program. Again, save this file. Run this file. Actually, I am going to show you one more thing in the Testbench as well, that using this real keyword we can also define our clock period. So what we are doing is we are going to say this is our clock period, 20 divided by 2 is going to be 10, and we are going to say use this variable inside this for our loop. This is just another way to define our clock. This line is equal to this line is equivalent to this line. Using this real word we can define or set some timing as well. Drag all these signals into the wave window. Run the program. And now we are going to see the same kind of waveforms, but using the number of clock cycles delay. Same waveforms you see. 1 clock cycle delay, 20 nanoseconds, 2 clock cycles delay, 3 clock cycles delay. Fourth is going to get 4 clock cycles delay, and after that all are going to go to 0 due to reset is equal to 1. So this is the way actually you guys can use the number of clock cycles to give the delays to your signals inside a system Verilog program. And actually you can play the way you can make your zero logics, right? So we can say make the zero logic or give the zero signal to your this load logic using this. Let me comment out these lines and start from the, we can say that make your other signals equal to 0 using some other stuff. So now we are making these other signals equal to 0 using the same kind of a statement here. So we are saying that after repeating 0 clock cycles, make all these equal to 0. But we can also say that after 1 clock cycle, make these signals equal to 0 again, 2 clock cycles or 3 clock cycles. But this is equivalent to right now these above 3 lines, because we are not repeating or giving any number of clock delays or clock cycles delay, but we can change these delays as well, just to make your program more flexible. Same way, come here. We are going to say, actually, not copy, comment out these lines. And we are going to see, do this. Uncomment. So this is the way actually you guys can play with your signal levels up or down. after number of clock cycles. So now our program is complete. The same logic we are going to get. So let's run this program again. So you guys can see the same waveforms. You see, these are just different ways to give timing delays to your signals, output signals. So end simulation. And now we are going to flip over to our VHDL program, and we are going to see how we can give the timing delays using the time units as well as the number of clock cycles to our VHDL output signals. So let's close these windows, open these, and now open these program or the project file as well as its testbench file. So first of all, we are going to see our main program. On the same pattern, we have defined first of all our entity. These are the libraries. This library we are going to use because we are going to convert our bits into integer, the PC bits. In the Verilog or system Verilog, you can just directly convert those, but here you have to use a function inside VHDL. So entity name is also same. The inputs and outputs are also same. Clock input, PC input, same number of bits, reset signal, and then 4 outputs, single bit. And then inside this architecture, what we are going to do is we are going to say begin, and then we are going to say process all whatever the inputs we have, and then we are going to say first convert the PC bits into integer, and then we are going to use those integer values inside this clock signal. We are going to say if reset equal to 1, make all the output signals equal to 0, and else we are going to say if reset is now equal to 0, no longer applied, check the values of the PC. If those are between 0 to 500, ALU logic 1, all other logics equal to 0. And then we are going to say if those values are between 500 to 600, load logic, all other logics equal to 0. And then we are going to say else if store logic, then if the values actually are between 600 to 700, then we are going to say implement store logic, make all other values equal to 0. And else we are going to say if the PC is, or the PC address range is above 700, we are going to say implement branch logic and make all other logic values equal to 0. Simple program, same program. And now we are going to see its test bench as well. So in the test bench, what we are going to do is we are going to say define test bench And in its architecture, we are going to call this component, which is our main program, RTL code, same inputs and outputs. Then we are going to define signals related to the inputs and outputs, same number of bits. And in this begin, we are going to call this component again port map. This is the way we implement in our VHDL programs. And in this process block, we are going to define clock like this, same clock of time period 20 nanoseconds. And in the second process block, we are going to give our PC values. First of all, we are going to reset. Then we are going to make reset equal to 0 and PC according to our ALU logic, then PC according to our load word logic, then PC value according to our store word. And then we are going to say branch, and then we are going to reset again all the signals equal to 0 using this reset equal to 1. Same program, both programs are already compiled. Let me just show you first the output so you can see its behavior too before giving these signals the timing delays. So you see same kind of inputs and outputs we are going to see. So here reset is equal to 1. So all the outputs are 0. Here reset is becoming 0. ALU logic, first of all, we are getting 1 according to our this PC value. Then according to our the second PC value, we are going to get the load logic equal to 1, then store logic, and then branch logic. And then whatever is the PC value, we are going to say if reset is equal to 1, make all the outputs equal to 0. So now let's try to give the delays to these signals according to our time units first in VHDL. So we are going to comment out these lines, comment this line, include this line. So give the delay of 20 nanoseconds using this after. And then we are going to say delay this load logic signal with 40 nanoseconds. And then we are going to say delay the store logic signal with 60 nanoseconds, and then branch logic signal we are going to say delay with 80 nanoseconds using this after you are going to see and this time units. So this is the way we can implement all those delays. Save this file. Simulate this. So now you guys can see the same output with the delays. So here we are going to say delay this after 20 nanoseconds. It is going to become 1 after 40 nanoseconds. This is going to become after 60 nanoseconds. This is going to become 1, and then after the 80 nanoseconds this signal is going to become 1, and after that, due to reset signal, all the signals are going to become zeros again. Now let's see how we can implement these delays using the number of clock cycles in a VHDL program. So in order to do that, we are going to define another variable. This is our clock period. We are going to say clock period of type time is 20 nanoseconds. So same clock cycle delay which we are going to give inside the Testbench program, we are going to give that here as well, because in VHDL we can't use the same clock which we are going to get from our Testbench program. So we can define a variable using the same number of time units here, and those we can use. Now we are going to use that clock period, and we are going to say after one clock period, you see 1 multiplied by clock period, make it 1, and then we are going to say skip this line, include this line after 2 clock periods. Now we are going to say after 3 clock periods, 3 multiplied by this, and then after 4 clock periods we are going to say make branch logic equal to 1. Same kind of delays we are giving, but using different approaches so that we can understand what our code is doing, what kind of delays we are giving. So this is the way we can implement the number of clock cycles delay. Simulate. And now you guys can see the same output, same number of cycles delay, 1 cycle delay, 2 cycles delay, 3 clock cycles delay, and 4 clock cycles delay to the last signal, and then after that all are becoming equal to 0. So this is the way you guys can play with the delays of your signals using VHDL as well as system Verilog programs. And using this clock period, you guys can implement the 0 number of clock cycles delay on these signals as well. Like in our system Verilog program, try to do that as well, that after number of clock periods you are going to say make these signals equal to 0, certain clock period signals, right? But the main thing now I am going to tell that always remember this sensitivity list inside this main process block. I mean, this process all means all the inputs are going to get included in our sensitivity list, not just these 2 inputs. But let's skip this and try to run this and see how the behavior would change. This is very important as far as the signal delays are concerned in VHDL and Verilog, and that's why I am going to tell you this thing at the last. So we have changed this process sensitivity list. Only clock and reset are applied here. Simulate this program. And now let's try to see if something changes. But you guys are going to see nothing changed due to the sensitivity list inside a VHDL program. So remember this thing. But now let me show you an interesting thing using the system Verilog program. So we are going to close this program and again open that system Verilog project. So let's close these both files and try to open these system Verilog files. So now our both system Verilog files are open, and let's go to this main project file and try to do these similar changes. So here previously, like the VHDL program, in the sensitivity list of our always blog, what we are going to do, we were doing here, we were including all the inputs here, right? But let me show you what would happen if we change always sensitivity list with this one. So we are going to use now only the clock signal. Or what we can do is we can actually include both, so that no need to waste the time, and include both the clock and the reset signal. So something changes. Compile this program. And now let's go to simulation. So now the sensitivity list of the system Verilog and VHDL program work a bit different ways, and that's what you guys are going to see now. So you can immediately see the waveforms have changed. You see, delay we are going to get of 1 clock cycle, but look, this delay is going inside this second program counter of load word as well, right? And then we are going to say, okay, this load logic is going to get 1 after 2 clock cycles, but this is going to also go inside this third store logics. You see, store logic in this period is becoming 1 here after 3 clock cycles, but look, this signal has shifted towards this as well. And same way, fourth signal is becoming 1 here after 4 clock cycles, but look, this third signal is coming inside its boundaries as well. And look, this one, even if we are making the reset equal to 1, this signal is still 1 and it is becoming 0 after these many clock cycles. So you see how the sensitivity lists in VHDL and Verilog behave. So in the case of system Verilog program, you have to very carefully select this. You have to include some statement like this, always at star. You see, rest of the code is same. We are making all these signals equal to 0, but they are becoming zeros after some time, not immediately. So remember this thing, So now I hope you guys have enjoyed this video. Have fun.